So we are going to start with analysis of variance, which is ANOVA. You must have heard of ANOVA from 2023, 21, 22, one of those classes that we remember. No, that's okay. So analysis of variance naturally would involve variances to analyze whatever effect that we're trying to observe. The regular analysis of variance that you would have seen in 2023, some professors cover it, some don't here, so I understand, is to compare multiple treatments. So if you have a two sample t-test, you compare only two samples. But if you have multiple samples from multiple treatments, anything over 3, greater than or equal to 3, we use ANOVA. Now you may ask, well, could I not compare things pairwise? Well, you can, but power is not going to be good. I'm not going to get into the power. So ANOVA, anytime you have more than 3 treatments or 3 or more, we'll use ANOVA. So if beta 1 is equal to 0, then the slope is not significant in the model beta naught plus beta 1 x. If that is statistically 0, then that entire term is going to go away. If that goes away, then we can conclude that y and x are not related, and whatever model that you observe is not significant. So if you do not reject null, that would imply 2 things. They are equivalent. So y and x are not correlated. That's equivalent to saying the fitted model is not significant. And if you're particular about finding the interval, the confidence interval for beta 1, will contain 0. Yes.
For the first thing you wrote there, is it fair to say that they're not correlated at all just based off this, or can we only say that they're not correlated linearly?
Linear. Because you could have a correlation, which is not linear. All of this is fine. So why do we need analysis of variance? Well, analysis of variance is yet another powerful statistical test, which we can use to determine significance for model that we fit. And not only that, here I have only one predictor, which is x. But what if you had more than one? Suppose x1, x2, x3, x4. We have a multiple linear regression model. And just like the t-test, where you compare only two samples, here, if you have more than one predictor, you can't use the t-test. it is painful because you've got to do repetitive things, and from a statistical standpoint, it will not give you a good conclusion. So I'm going to start with ANOVA for the simple case, and we will extend it to multiple regression in chapter 3. That makes sense. In practice, the simple case, do we need an ANOVA? No. A t-test will suffice. Using that confidence interval will suffice. But when we get to multiple linear regression, the only way is to look at an ANOVA. Good. So what is it? Well, clearly, analysis of variance, so it must have variances. What is yi? That's an easy question.
Observe.
Observation of y, whatever y might be. What is y bar?
Sample mean.
Sample mean of y. So I have yi minus y bar, and I'm going to do some silly math here. Did I make a mistake? Did I do something that is not reasonable? Nick? No, we didn't.
Can't get any worse.
No, right. Thank you. It did that. yi minus yi hat. So adding, subtracting, I simply added a 0. What is that expression? What is it? That's the residual. That is the residual. Very good. So the distance between the actual value and the fitted value. Now, over here, I have yi hat, the fitted value minus y bar. I'm trying to say how far the fitted value is from the average of one. You will see as to why that matters when I derive this. So residual, another expression, and yi minus y bar. What I'm going to do is I'm going to square on both sides. Good. Okay. What would that be? Algebra. A plus b squared is a squared plus b squared plus 2ab FOIL. So yi minus yi hat square, yi hat minus y bar square. Two times yi minus yi hat times yi hat minus y bar. Good. As of now, we're simply looking at the height of observation. But I can't simply look at one arbitrary observation. I've got to look at all observations and would want to know what happens overall. So what should we do if I have to take into account all the observations and measure variability? We did this earlier. Eric,
Summation.
we just sum over all values. Good. And that part is still the residual. I think it records it E sub 5. Wow. We'll call it EI or epsilon I, that's my detection. So epsilon I, EI, one and the same. I like epsilon I. The book uses EI. Good so far. Erase. Going to leave the first term as is. The second as is. We'll get to that in a bit. The last sum, I will take the 2R and I like epsilon I, so I'll put it as epsilon I times yi minus yi hat. Good. That part, I can distribute the epsilon I. Agreed. Yes, distributed through twice. Thank you. It's yi hat minus yi. This part I will simply distribute. I don't want to rewrite all the first, so I'll write it as a note. 2 I distributed epsilon I, distributed the sum, and that's what's on that. So if you multiply the fitted value by the residual and sum over all possible epsilon i's, theoretically, that is 0. If you take the average of y multiplied by all epsilon I, theoretically, that would be 0. In practice, it would be extremely small. So that entire term over there would equal 0. Good. So the third term would simply disappear. So, what does each of these sums remind you of? When you look at that formula, it should remind you of something else that you've done before. Huh?
Euclidean differences.
Great, statistically. That is correct, but in statistics, what do we call that? Sum of squares, great. What else? Sum of squares is proportional to something. Give you a hint. Start with the letter V. Variance. So how do we find the variance? We simply take, for instance, yi minus y bar squared is simply the numerator part of the variance. Yes? And I divide it by n minus 1, the entire formula for variance comes into play. So the numerator is the sum of squares, the denominator is degrees of freedom. You simply end up getting the variance. I took whatever net variance that I have, that is the variance in y, do we agree? So if I divide that by n minus 1, that'll be the variance of y. So that is the total sum of squares. Why do we call it the total sum of squares? It is the total variability in y. And we want to know how that going split. So we split it, or we decompose the total sum of squares into 2 parts. That part has a name. That is something you should know, hopefully. yi minus yi hat is the residual. I squared it, so I have squared residuals. I'm summing it over all values of I, so that only leaves us with one option of squared residuals. Sum squared residuals. This is simply sum. Good. So the total variability is decomposed into two parts, sum of squared residuals, and this remaining part over here. This is the part that you obtain from the regression line. Why? We know that the regression line will pass through blank. January centroid. So it will pass through the centroid. So I'm seeing how each fitted value is away, or how far away they are from the centroid. So I am simply looking at the sum of squares that I get from the fitted regression model. So this is SSR. Good. With a plus in it. So total sum of squares decomposed into two parts, SS res and SSR. Well, they're all proportional to variance, correct? So what am I doing? I'm simply analyzing variances. Would you agree? Hence the name analysis of variance. Okay. So total sum of squares is always equal to the regression sum of squares plus SS res. If I divide SS res by n minus 2, what will I get? Sum divided by n, always average. So you would get mean. So MS res. In a similar manner, you would have MSR, MST. But I'm not going to do that here because algebraically it could get confusing. So I'll just leave it as is. Okay. So one may ask, well, what is the point of all of this? Well, what would happen if that became 0?
SS res would equal SST.
Rate deduction there, SS res would equal SST. What will that mean? The total variability in Y is equal sum of squared residuals, again, rate deduction. But what would it mean in the context of regression? What does that tell you about the model?
All the variability is caused by error.
Very good. Every the entire variability that you see in YI is purely explained by error. Hannah, did you have an answer?
I was going to say, but it doesn't pass through the centroid.
Okay, it doesn't pass through the centroid. In other words, this becomes useless. If this part becomes useless, it becomes 0. Whatever variability you have is just error. And would that mean that the model is useful?
It should be useful.
It should be. So if any variability that you see in your Y values is simply noise,
So we did.
there is no underlying pattern, it's just noise.
There's no correlation.
There is no relationship at all. The regression has no use. If this goes away, all I have is something or variability that's proportional to noise, and that would be the variability that you see in I. So this part is useless, which would mean the regression model is useless. Good. But would that be 0 always? In practice, do we expect this to be exactly 0? No. Theoretically, yes. In practice, it is going to be some number our objective now is to determine, well, how far should it go away from zero for me to conclude that SSR is useless. Does that make sense? That is the entire purpose of hypothesis test. Because in statistics, 1.2 doesn't exactly equal 1.2 because we are looking at variability. So theoretically, zero here would mean we don't have a significant movement. In practice, it is going to be some non-zero value. And our question is, how far should it go away from zero for us to conclude that the regression model is useless? Linear regression. Good. Okay. I will have to omit a few details because it's theoretical. If you want to know, I'll talk to you. I'm going to write a table.
So could you run that by me one more time? So you're saying that if the sum of squares for regression is 0, that tells us that the variability all depends of the noise.
Yes.
Constant. Then what does you say that it does with the model? That does that mean that the model is useless? I mean, that's appropriate.
So if whatever variation that you see in Y, let's say you're measuring height of P, and that is our Y, and it depends on the weight of the person, right? Bunch of people. If there is, in fact, a correlation, a line, then I can say whatever variability that I see in height is due to the variability in weight. But if I can't come up with a line, and if that line is useless, then height is not related to weight. But you still have variability in the heights to your weight.
Correct.
Because not everyone is of the same height. So that variability would correspond to purely noise, because height is not related to weight. Does that make sense?
Yes.
So whatever variability that we see in Y, in my example, the heights, cannot be explained by the weight of the individual. If that is the case, and if you know that there is variability, this is something that you cannot explain. Well, what you cannot explain is noise. Right? Okay. Later on, when I get to R squared, I will write this again. This part is what we call unexplained variation. Things that you cannot explain. What makes something random? Well, noise. And can you explain noise in a deterministic sense? No, I don't know. This part is something that I can't explain. Explained variation. Just like now that we went through Hurricane Ian, the path of Hurricane Ian, we all knew that Florida is going to be screwed somehow, but we just did not know where it's going. Yes. Eventually, we narrowed it down and we said, okay, the path is going to be southwest Florida. Yet there was some wiggle room, which we didn't at this time. So we were able to explain a good amount of it, but we didn't know until the very end as to where it is going to be. So that tiny bit of fluctuation that you do not know is the unexplained variation. Now, that I can write it as SSR. This part SS res. Naturally, if I sum those two, what will I get? SST. SST is yi minus y bar squared summed over all observations. If you divide that by n minus 1, what will you get? Variance. So the total degrees of freedom here has to be n minus 1 because that's the number you've got to divide by so that you get variance. Agreed? From last class, the class before, SS res has to be divided by something so that you get MS res. What is that sum at degrees of freedom? N minus 2. N minus 2. Good. And I gave an explanation as to why we put that 2 there. It's 2 because we are using 2 bits of information in estimating the unexplained part and the explained part, which would be beta naught and beta 1. 2 parameters. So 2. If you have 3 parameters, that would be 3. 10 parameters, that would be 10. Good. Okay. If I add those 2, I get that number. So if I add those 2, I should get n minus 1. So what should get back? 1. Good. Lovely. So we will generalize this to a multiple regression model in chapter 3. But I will put a note here so that you can connect later on. So that would correspond to the number of predictors. In other words, the number of x's you have. In a simple linear regression model, how many x's do we have? Just 1. So that would correspond to the number of predictors. That 2 would correspond to the number of parameters. In our linear regression model, what was that? That was beta naught and beta 1. Good. And why is that 1 less? Beta naught is just the intercept. It doesn't play any role in terms of estimating correlation. It's just there. Later on, I would do estimating a regression model through the origin. Well, we could just ditch that beta naught and simply keep beta 1. We'll get to it later. Are we clear so far? If I take SS spreads, divide by n minus 2, I am going to get MS spreads. Okay. SSR divided by 1 I will get MSR. I believe we call it as MSE, also mean squared error. One and the same. What does the mean squared error estimate? So variability in what in the error, it is going to be estimated using MSE. So in theoretical statistics, the distribution of variance is chi-squared. It will come back later when we do a confidence interval for variance. And theoretical statistics, chi-squared over chi-squared with appropriate degrees of freedom will be an F distribution. we can F it all up. So this part is simply F would, some people would call it as F ratio, some F test statistic, just like a T statistic, you have an F statistic. Social science is often called, it is often called or referred to as F ratio. Y ratio, we're going to divide those two. So MSR divided by MS res. Or MSD. I'll find that later. Typing somewhere else. Okay. What does the distribution of T look like? We did this last class. In other words, if I sketch the curve, what would the curve look like?
Kind of like a norm, but not quite.
Kind of like a normal distribution, but not quite. In other words, a T distribution would have a bell-shaped curve, but numerically not the same. If you are not following, you can just flip through your notebook, and the problems that we did in t-test, we always drew a bell curve, and then we did the projection region. Well, the center of the T distribution is 0, and you have a left-hand side, and you have a right-hand side. So you have negative numbers for T, positive numbers for T. Could F ever be negative? Why, Dennis? Dennis says no.
You're summing squares.
So sum of squares, a square cannot be negative, yes? So you have a positive number divided by positive number, result is always positive. 2023. If you have a distribution that is lopsided, in other words, all positive, all negative, we call it skewed distribution. In this case, it is right skewed. That's fourth way. Control that's good. And of course, it's going to go towards 0. Yes.
Is that related at all to the chi-squared? Because that kind of looks like a similar shape.
F has a distribution similar to chi-square. As I mentioned earlier, the numerator part, SSR, here, will correspond to a chi-squared. SS res, chi-squared. In general, variability, sum of squares will follow a chi-squared distribution. Chi-squared divided by chi-squared will have an F distribution. But in terms of shape, if you have two curves that look like a chi-squared, the result would look like a chi-squared. Okay. So 0 is over here. And if this number gets bigger and bigger and bigger, you're moving farther and farther away from 0. Do you agree? Now, for some alpha, what is alpha? Another name for alpha, sure, is the false positive rate. Another name. I'll give you a hint. Level of significance, the level of significance. Look in your notebook and tell me what did we use alpha for when we did a t-test. So alpha is the probability of type 1 error. It is also the significance level or level of significance. And if you look in your notebook, every single problem that we did for the hypothesis test, I sketched this out and I called that area to be alpha. And that number right there is the critical value as Dennis pointed out. And as Eric mentioned, anything past that critical value will be the rejection region. Well, if I'm talking about the rejection region, I first need a test definition. Do you agree? I did not write that test definition yet. So, in an analysis of variance for regression, the null is model. Let's see, use the basic principle of hypothesis testing and tell me, should I write it as significant or insignificant? Here. I'll give you a hint.
Significance.
Huh? No, why is that, Jeff?
Because just the null hypothesis is the statement that these are not.
But well, no hypothesis, by definition of a hypothesis test, null means nothing. Nothing means no regression, no effect, no correlation. So it has to be something, nothing, or that effect. Something that implies no effect. So we're talking about significance of that model. If it has no effect, this has to be insignificant. And we know the alternative is the opposite of the null, it's the opposite of an insignificant model. Is a significant model. Good. So that critical value, if you look in your notes last time, we called it T sub alpha over 2 df, and df is the degrees of freedom. What was that degrees of freedom for a t-test? -2. So last time it was n minus 2. We called it t because the distribution is t. Here, the distribution is f. So naturally, I should put f. So now sit here. We're going to f it all out. So f subscript 1 minus alpha, y1 minus alpha, area below is the area above is alpha, and the area under the entire curve is 1. The area below that line has to be 1 minus alpha. T distribution had 1 degrees of freedom, so we simply put df. How many degrees of freedom do you see here? Look at the table. And then it says 3 different df variables. What are the 3?
1 and -2 and
df1, df2, df3. Yes, 3 degrees of freedom. But we need only 2 of them. Again, there is involved. I'm not going to get into that. So df1, df2. Good. Could that number ever be negative? No. Again, positive distribution. Generally, you have that look. What's your question?
I was going through again that DF1, DF2 situation.
DF1, DF2. Good. If you have three variables, x's, you'd call it x1, x2, x3. Yes? DF1, DF2, DF3. But we're using only these two to find f, hence DF1, DF2. Let's see. Should we have a small f or a really large f to reject the null? Large. In other words, whatever value test statistic that I find here, if this number keeps on going in that direction, falls right over here, you went far enough from 0 for a given alpha. You would reject the null. If you reject the null, we go with the alternative. We found evidence to work the alternative. So the regression model is significant. That makes sense. Again, if we're not talking about randomness, if this wasn't statistics, then 0 means nothing, and anything other than 0 means something. Yes, but this is advancing statistics, obviously. So we have randomness. So 0 doesn't always mean, 1 or 1.2 doesn't always mean something. By all means, if you account for variability, 1.2 may be just the same as 0. Yes, because of variability. So this number is going to help us decide if that f is large enough for us to reject the null and conclude that whatever model that we have is significant. If I conclude that the model is significant, can I also conclude that y and x are correlated? Linear. Yes. Does that make sense? So we have a t-test to help us give the conclusion whether the model is significant or not. We also, you can use a confidence interval, but those two are useful if you have only one predictor. So you've got y, you have x. But if you have more than one x, you cannot use that. We need an ANOVA. And in practice, can you explain some random process using just one variable? I'll use the example that I used earlier, heights. And the height of a person be explained only by weight, or could there be other factors? Other factors are involved. So y, x, height, weight, not sufficient. There's probably a bunch of other stuff that we have to observe. Earlier, when I derived, I said SSR, if it becomes 0, then the regression model is useless. Yes? If that becomes 0, that becomes 0. Agree. So you will not be protected. If that is an extremely small value, you are dividing by degrees of freedom, it will be a small value divided by something, you will not protect because it will be small. But the interesting case is, let's say you have some number in the numerator. Give me a number between 2 and 4.
3.
Decimal. A real number.
2.77.
Okay, 2.771. 2.771 in the numerator. Denominator, say you have 99.82. Good. So 2.77 divided by 99.82, somewhere close to 0.02. Yes? Now 0.02 and put you close to zero, you will not reject, you will conclude that the model is insignificant. Why did I bring up that case? Well, even though you have some number 2.771, the effect of noise is significantly larger than the actual effect. So whatever that you're observing is garbage. Does that make sense? So noise is overriding whatever effects that you have, which would make F to be very small. Are we clear?